If I've got an object, whether it be a roller coaster cart or a bucket of water on a string or a set of keys on the end of a lanyard, it doesn't really matter. If I have an object at the top of a circle and it's upside down, what forces do I have acting on that object? Always. Like, let's forget about friction, because if some of you might say, well, friction could be there. Sure, friction could be there. But if it's a perfectly smooth surface, then maybe we can ignore friction, and that's what we'll do. What two forces will always be there no matter what? Kessler, what's one? Gravity is there. And which way does gravity act? Good. Gravity acts downward. Okay, what other force is always there no matter what? That is, if you're on Earth or on some other planet. Yep, Bruce? The normal force. And which way does the normal force act? Good. And do we know the normal force is bigger or smaller than, or the same length as the force of gravity? We don't know. It depends upon how fast the object is moving. But the bottom line is those two forces are always going to be there. You know what? Actually, I lied. I said those two forces will always be there. One of those forces will not always be there. Okay, there's one circumstance where it's going in uniform circular motion where one of those forces will not be there. Do you remember what that is? No normal force? When is it possible to have no normal force and still continue going in the circle? This is what we talked about on Thursday, right? Yeah. Yeah, when you're going at the minimum speed. We learned on Thursday when we're going at the minimum speed, we're going to set Fn equal to 0. In that situation, there is a normal force everywhere around the circle except for the top of the loop. At the top of the loop, the normal force is 0. It's gravity alone that's providing the centripetal force. But that's that one, that 1 in 100 case where you're going the minimum possible speed where the normal force is 0. Otherwise, the normal force will always be there. Okay, let's look at the bottom of the circle. Let's say you get this set of keys on the string, or you get this bucket of water on the string, or you get this roller coaster car at the bottom of the loop, or whatever the case may be. We have the same two forces acting here. Which way does gravity act now when we're at the bottom of the circle? It's going to act downwards. Gravity's always going to act downwards, right? No exceptions to that one. Gravity will always act, at least when we're on Earth, gravity is always going to act downwards, straight toward the center of the Earth. The normal force also acts here. Which way does the normal force act? That can change direction all the time, right, depending upon the circumstances. In this case, the normal force is upwards. How long do we make that normal force? We make it bigger, smaller, or same length, Kelly, as the force of gravity. It's going to be bigger, because if you're going in the circle, if you continue to move in a circle, then the net force must be toward the center of the circle, and therefore the upward force must be bigger than the downward force. All right, in both of these cases, we would say F net is equal to the sum of the forces. That would be Fg plus Fn. In both cases, we would say mv squared is also F net, is equal to the sum of the forces. And then we got to worry about positives and negatives. At the top of the circle, is the force of gravity positive or negative? Negative because it's acting down. At the top of the circle, is the normal force positive or negative? Negative because it's acting down. At the top of the circle, is the centripetal force, that is the net force, the total force, positive or negative? Negative because it's acting downwards. Good. And at the bottom of the circle, things change a little bit. At the bottom of the circle, is the force of gravity positive or negative? Logan, is the force of gravity positive or negative? Gravity is always going to be downwards, right? So we're going to make it negative here. Is the normal force, Kaylee, is the normal force positive or negative? Because it's acting good. And at the bottom of the circle, is the centripetal force, Jillian, positive or negative? It's positive because it's acting upwards, right? The net force is toward the center of the circle. Same direction as the normal force, so it's going to be positive. Good. One more little thing, and this is what we talked about on Thursday, right? We kind of alluded to this earlier here. There is one situation where there is no normal force, and that's when you're traveling at the minimum speed. So when you're looking for the minimum speed, what you need to do is set Fn equal to 0. In other words, mv squared over r will be equal to m times g. Solve for v, that is the minimum speed. Go faster than that, you're fine. Go slower than that, and then you're going to fall out of the circle at the top of the circle, right? It's going to be at the top, right? If you're going to fall out, it's going to be at the top. Okay, so you're going to be analyzing the top and then set Fn equal to 0 and do your thing. All right, we had a couple questions for homework, page 262. I want to do at least question number 2 here. Do we need to do number 1 as well, or are we good with just number 2? Who wants number 1 gone over? Okay, number 1 and number 2 will do. Number 1 says, neglecting friction, what is the minimum speed a toy car must have to go around a vertical loop of radius 15 centimeters without falling off? I'm going to circle this because I don't like centimeters. I know I'm going to convert that to meters. Vertical loop, minimum speed. We know we're going to analyze the top of the circle where we have gravity acting down and the normal force acting down. But we know what? We know what is the case when we're looking for minimum speed. Fn is equal to 0, right? Some of you will just not even write that out. Just write down mv squared over r is equal to m times g, and that's okay. I like to write out the whole thing and then cross off Fn just to stay in the habit of including the normal force, right? I don't want to forget it some other time when I can't cross it off. Fnet is also equal to mv squared over r. Fg is m times g. Cancel out the mass there, which is good because we don't know how heavy this toy car is. Sub in our numbers now. Looking for v. Got the value of r, it's 0.15 meters, and g is 9.81. Now, technically, both sides would be negative here because they're both acting downwards. But in this case, if you forget it, you're gonna get away with it, right? Because it cancels. 9.81 times 0.15. Take it up by multiplying, then square root. We do our thing there, and we should get 1.21 meters per second. Second question says, what is the maximum radius a roller coaster loop can be if a car with a speed of 20 meters per second is to go around safely? Maximum radius is really the same question as minimum speed. Because you can imagine, if I slow down the car, then at some point it's going to fall out of the loop. Well, if I keep it at the same speed, but keep increasing the size of the circle, then you can imagine you're going to end up with the same effect. It's going to fall out of the loop. Well, what happens when it falls out of the loop, or begins to fall out of the loop? The normal force is 0. So really, this is the same question as question number 1 is. We're just solving for a different variable here. We're given a speed here. We need to solve for the max radius. So we're going to say, at the top of the circle, net force is equal to Fg plus Fn. But we're going to say Fn is equal to 0. mv squared over r is equal to m times g. Cross off the masses, which again is good because we don't know how heavy this roller coaster is. We got v this time. 20 squared over, we're looking for r, equals 9.81. Since we subbed in numbers here, I'm going to make sure we include the sign. They're both negative, even though we could get away without putting those in this one. Well, this one's tricky, eh? Let me solve for r there. What do you got to do first? If r is on the bottom and we want to find r, what do we got to do with it first? Alex? Multiply by r to get the r on the top, right? You need, the variable you're solving for, you need to be on the top. So Alex said we multiply both sides by r to get on the top. That's exactly what we do. We're going to say, by the way, we're going to cancel out the negatives. 20 squared is equal to 9.81 times r. Well, now it's pretty easy, right? Now what do we do? Divide by 9.81. So we get 20 squared, which is 400, divided by 9.81 gives me the value of r, and that is 40.8 meters. So you can go 20 meters per second around this loop and not fall out. If you go slower than 20.8, you're going to fall out. Or if you increase the radius above 40.8, so if you go below 20 meters per second, you're going to fall out. If you go above a radius of 40.8, then you're going to fall out. Okay, the magic numbers: 20 meters per second, 40.8 meters. Hey, if you decrease the speed or increase the radius, then you better make sure you have your will done up. Good. All right, I want to give you a few minutes to get back into the week here by working on some questions on page 268.